Welcome to MathVare. Today we're exploring the very foundation of mathematics, the field axioms. These 6 elegant axioms are the building blocks from which all of algebra emerges. By the end of this video, you'll understand how seemingly simple rules create the entire structure of real numbers. Let's begin with a fundamental question. What exactly is a real number? We work with real numbers every day, but what properties define them? The answer lies in 6 axioms that describe 2 operations: addition and multiplication. The field axioms are divided into 6 fundamental rules. Let me introduce them one by one. Axiom 1 is the commutative laws. For addition, we have x plus y equals y plus x. For multiplication, we have x times y equals y times x. This means order doesn't matter. Whether you add 3 plus 5 or 5 plus 3, you get 8. Whether you multiply 4 times 7 or 7 times 4, you get 28. The commutative property is intuitive, but it's not true for all mathematical operations. Axiom 2 is the associative laws. For addition, x plus the quantity y plus z equals the quantity x plus y plus z. For multiplication, x times the quantity y times z equals the quantity x times y times z. This means we can group operations differently without changing the result. When adding 2 plus 3 plus 4, we can compute it as 2 plus the quantity 3 plus 4, or as the quantity 2 plus 3 plus 4, and we get 9 either way. Axiom 3 is the distributive law. It states, x times the quantity y plus z equals x times y plus x times z. This connects multiplication and addition. It's the rule we use when expanding brackets. For example, 3 times the quantity 4 plus 5 equals 3 times 4 plus 3 times 5, which is 12 plus 15 equals 27. Axiom 4 is the existence of identity elements. There exist 2 distinct real numbers, 0 and 1, such that for every real x, we have x plus 0 equals x, and 1 times x equals x. 0 is the additive identity, because adding it doesn't change the number. 1 is the multiplicative identity, because multiplying by it doesn't change the number. Axiom 5 is the existence of negatives. For every real number x, there is a real number y, such that x plus y equals 0. This number y is called the negative of x, written as negative x. For example, the negative of 7 is negative 7. Because 7 plus negative 7 equals 0, Axiom 6 is the existence of reciprocals. For every real number, x not equal to 0, there is a real number y, such that x times y equals 1. This number y is called the reciprocal of x, written as x to the negative 1, or 1 over x. For example, the reciprocal of 5 is 1/5. Because 5 times 1/5 equals 1, these 6 axioms might seem simple, but they're incredibly powerful. From them, we can prove every algebraic rule you've ever learned. Let me show you how. Let's prove Theorem 1.1, the cancellation law for addition. It states, if a plus b equals a plus c, then b equals c. This seems obvious, but we need to prove it using only our axioms. Here's the proof. By Axiom 5, there exists a number y such that y plus a equals 0. We call this number negative a. Now, we're given that a plus b equals a plus c. Since sums are uniquely determined, we can add negative a to both sides. On the left side, we get negative a plus the quantity a plus b by the associative law from Axiom 2. This equals the quantity negative a plus b, but negative a plus a equals O. By the definition of negative a, so we have 0 plus b. By Axiom 4, this equals b on the right side. We perform the same steps. Negative a plus, the quantity a plus c equals the quantity negative a plus c, which equals 0 plus c, which equals c. Since the left side equals the right side, We have B equals C. This proves the cancellation law. This theorem has an important consequence. It shows that the additive identity 0 from axiom 4 is unique. There's only one number with this property. Now let's prove theorem 1.2, the possibility of subtraction. It states, given A and B, there is exactly one x such that a plus x equals b. This x is denoted by b minus a. Here's the proof. By axiom 5. There exists a number y such that a plus y equals 0. Now let x equal y plus b, then a plus x equals a plus the quantity y plus b. By the associative law, this equals the quantity a plus y plus b. Since a plus y equals 0, this becomes 0 plus b, which equals b by axiom 4. Therefore, there is at least one x such that a plus x equals b. But by theorem 1.1, the cancellation law, there is at most one such x. Therefore, there is exactly one. This proves that subtraction is always possible and unique. Let's prove theorem 1.3. It states, b minus a equals b plus negative a. This connects subtraction with the addition of negatives. Let x equal b minus a, and let y equal b plus negative a. We want to prove that x equals y by the definition of b minus a. We know that x plus a equals b. Now consider y plus a. This equals the quantity b plus negative a plus a. By the associative law, this equals b plus the quantity negative a plus a. By the definition of negative a, this equals b plus 0, which equals b by axiom 4. Therefore, x plus a equals y plus a. Both equal b. Hence, by the cancellation law from theorem 1.1, we have x equals y. This proves that b minus a equals b plus negative a. Now let's prove theorem 1.4, the negative of negative a equals a. This might seem obvious, but we must prove it from our axioms. We have a plus negative a equals 0 by the definition of negative a. But this equation tells us that a negative of negative a, by definition, the negative of negative a is the number that, when added to negative a, gives 0. That number is a. Therefore, negative negative a equals a, as asserted. These proofs might seem tedious, but they demonstrate something profound. Every algebraic rule you use, from combining fractions to solving equations, ultimately rests on these 6 simple axioms. Mathematics isn't just calculation. It's a logical structure built from fundamental principles. Let me show you one more important theorem. Theorem 1.6 states, 0 times a equals a times 0 equals 0 for any real number a. Here's why. By axiom 4. We have 0 plus 0 equals 0. Multiply both sides by a, using the distributive law from axiom 3, a times the quantity 0 plus o equals a times 0. This gives us a times 0 plus a times 0 equals a times 0. By axiom 5. There exists negative a times 0. Add it to both sides. On the left, negative a times 0 plus the quantity a times 0 plus a times 0 equals the quantity negative a times 0 plus a times 0 plus a times 0, which by the associative law equals 0 plus a times 0, which equals a times 0. On the right, negative a times 0 plus a times 0 equals 0. Therefore, a times 0 equals 0. Understanding these axioms gives you a deep appreciation for the structure of mathematics. Every algebraic manipulation you perform is justified by these fundamental rules. If you found this exploration fascinating, don't forget to subscribe to MathVare for more deep dives into mathematical foundations. Now, here's your challenge. Using only axioms 1 through 6 and theorems 1.1 through 1.4, prove the following statements. Challenge 1. Prove that negative the quantity a plus b equals negative a minus. Challenge 2. Prove that negative the quantity a minus b equals negative a plus. Challenge 3. Prove that if A is not equal to 0 and B is not equal to 0, then the quantity A times B to the negative 1 equals A to the negative 1 times B to the negative 1. Write your proofs in the comments below. Good luck, and I'll see you in the next video.